next. Manometers. The most common way we have of measuring pressure is a manometer, which is a piece of pipe with liquid in it. When you blow down on one side of that bit of pipe, the liquid rises in the other bit. If you want a really accurate manometer, then what you do is you tip it over, and then the water's got an easier job climbing. So it's called an inclined manometer. It gives you much more accuracy. Of course, you get less range, but you get greater accuracy. Bourdon tube. Now, what a Bourdon tube is it's basically a bit of tube that's closed at the end. And there's all sorts of explanations about how a Bourdon tube works, and they go into the fact that the outer part of a Bourdon tube has got a larger surface area than the inner part of a Bourdon tube, so that when you do the equations and the mathematics, it proves that the Bourdon tube straightens out. My explanation for the way a Bourdon tube works is that a Bourdon tube is exactly the same as those things you get in your party bag, or your children's get in the party bags. You know, the sort of things, they're all curled up, and when you blow in them, they go straight, and they make an amusing noise. Now, a Bourdon tube is exactly the same. You blow in it, and it straightens out. You'd have to blow in it bloody hard for it to make an amusing noise, but it works on the same principle. You blow in one end, and it straightens out. It's as simple as that. If you want more accuracy, you get a longer bit of tube. And then you just have a few little, how do you wind up a longer bit of tube? You can either wind your longer bit of tube up into a big spiral, or you can wind your longer bit of tube up into a helix, which is a spring. But really, it's just exactly the same things as you get in the party bags. You blow in at one end and it straightens out, to the amusement of everybody. Different types of capsules. This is another way of measuring pressure. Basically, you get a couple of bits of metal, flat bits of metal. They look very like the ends of baked bean cans. And you weld them together with an air gap between them, or you maybe fill it up with a liquid. And as pressure changes, they're just like balloons. They inflate and deflate. And all you have to do is measure how much they move around, and you've got the pressure. To do this, what we do typically is you attach some kind of mechanism to one end. I'll draw that in red. You attach some... Oh, that didn't change. Change to red, damn you. Right, you attach a mechanism to one end with some kind of lever that then moves an arrow around. And that gives you the pressure. All of these machines, the Bourdon tube and the capsule, they're both, they're both mechanical. And they have a tendency to stick. So if you want to get an accurate reading off them, what you have to do is you have to go up and kind of tap them. And you give them a little tap, and they'll move to their correct position. But they all have a slight tendency to stick. And if you're ever calibrating one of these, bear that in mind. You might need to give it a little tap, because it's always funny when somebody's calibrated a Bourdon tube, and I go up to it and I say, give me 2,500 kPa, and they do it, and then I tap it, and the needle moves by 5 millimeters. So that's something to bear in mind. If we want to get an electronic value for a pressure transducer, we need to have an electronic way of taking that pressure in. Nowadays, there's a few ways of doing that. There's several different types of resistance pressure transducer. There's capacitance pressure transducers. There's inductance, because capacitance and inductance, you may not know this, but inductance is capacitance's evil twin. from the alternate universe. And wherever you see capacitance, you always see inductance, and it's always thinking evil thoughts. And you can tell the difference because inductance got a little goatee beard. Anyway, enough of that. Resonant wire, which we'll go into, piezoelectric, which is a good one, and there's also optical type pressure transducers. So we'll look at those in order. The first one, the first type of resistance pressure transducer is what we call the strain gauge. This is a tiny, tiny little piece of copper foil etched onto a very thin piece of plastic. And what you do is you glue this onto the thing that you want to measure the pressure in, or the strain in. And because the copper is so thin, if we were to compress the copper, then the resistance goes down. If, on the other hand, we stretch the copper, the resistance goes up. So all we need to do is measure the resistance, and we know the amount of strain on there. And strain is related to pressure. We tend to do this using things called load cells. A load cell is basically a chunk of metal or a chunk of plastic that we've stuck a couple of strain gauges on. And load cells are what we use for weighing things. So, you've probably seen load cells. Load cells are what's in scales. Nearly every set of scales nowadays has got a load cell in. We use it for weighing people, weighing trucks, weighing suitcases, and weighing tanks. If you can weigh, not army tanks, but tanks full of liquid. If you can weigh a tank full of liquid, you know how much is in it. Here's a cutaway of a load cell, of different types of load cells. And here's where we're using a load cell to weigh a tank. The next type of resistive pressure sensor I'll talk about is the piezo-resistive pressure sensor. Now, piezo doesn't mean crystal. Piezo means to press. Although most people nowadays think piezo is related to crystals. Right, what a piezo-resistive pressure cell is basically a piece of silicon. You get a little bit of silicon, a tiny bit of silicon chip, and you measure the resistance across that silicon. When you squeeze that silicon, the resistance goes up. So you can tell how much the silicon is being squeezed by how much the pressure goes up. Piezo-resistive pressure sensors are, well, they're excellent. They're absolutely excellent. They're very susceptible to other things that might do squeezing, like temperature might squeeze the piezo. Vibration might cause bad readings, because vibration looks like a whole load of pressure coming and going. But if you can get round those small factors, and the fact that it's not particularly linear, then the piezo-resistive pressure sensor makes an excellent pressure sensor. Here's a cutaway of a standard piezo-resistive pressure sensor. They look a bit like spark plugs in a car. One thing about silicon is it's very, very tough. It'll take high temperatures. It'll take high pressures. The transducers themselves are tiny little things. They're this size. They are minuscule. So you can build them into very small things. Here's the standard, or a standard application for a piezo-resistive pressure sensor. We use them for measuring things like oil pressure in a car. We could also use them for measuring. You can have one of these in each one of your cylinders, and it will give you the compression occurring in the cylinder. That's what they have in Formula One cars, so they can tell exactly how the Formula One car is performing. And they can dynamically alter the engine performance by seeing how the engine is performing remotely. So piezo-resistive pressure sensors will take huge pressures, massive pressures. They'll take huge temperatures. They're not necessarily the world's most accurate pressure sensor, though. Another type of pressure sensor, and now we're going into the realms of things that were tried but were stupid. Another type of pressure sensor was the potentiometer pressure sensor. And you can see how it works. As the pressure in the bellows increases and decreases, it pushes a little arm up and down, which we attach to a Wheatstone bridge. Good old Wheatstone bridge. As I've probably told you before, the only place you're going to see a Wheatstone bridge nowadays is if you happen to be walking past the River Wheatstone and you see a bridge over it. Nobody uses Wheatstone bridges anymore apart from TAFE. So that's one thing that was tried and was dismissed as silly.